where I use a review for yesterday lecture. Yeah. We have studied about the photoelectric effect. So this phenomenon known as photoelectric effect was discovered by Henry Hertz, and then characterized by Reinhardt. Yeah. So Reinhardt basically he studied further the discovery of this Hertz, yeah, Henry Hertz. So basically, this is the picture. Okay. So basically, we have this emitter and this is a collector. Okay. This is an A is an ampermeter. V is this voltmeter. Okay. And V external is variational EMF, yeah, electromotive force, the source potential. Variational, yeah, potential, external potential. Okay. So basically, so when the light, for example, illuminated this, so this emitter basically made from the metal. Yeah. Okay, so basically the light illuminated this emitter, or this light falls into the surface of this emitter, and then the electron that released from this emitter, this emit ya, emitter ya emit ya, memancarkan ya, artinya in bahasa yang memancarkan. So we have this is a vacuum tube, okay, and we have these electrons somehow released from this emitter goes to collector, okay, because this is the direction of electron from the left to the right, so it should be the current should be from the left, from the right to the left, okay, this one. So somehow this current will detected by this ampermeter, okay, and we have also detect, because we have detect also ampermeter, so it should be there is a potential difference, yeah, between this point and this point, okay. Okay, so basically, so we have the current, okay, and then if we want to stop the current, okay, the current, so it means that the ampermeter shows 0. Okay, so it should be, we have to set this external voltage such that we have this current is 0. Okay, this is we call it stopping potential. So somehow we can set external potential such that there is no current flow, okay, in this circuit. So it means that if the current is 0, it means that the electron have maximum energy, okay, has maximum energy equals to E, this, which is the unit charge of the electron, and times Vs, yeah. Vs is the stopping potential. So this we can know this Vs from this external. Okay, so this is basically the photoelectric effect. Is there any question? Okay, so this is, we call it walk function. Yeah? For example, for natrium, aluminium, cobalt, cuprum, zinc, argentum, silver, PT, platina, yeah. PB is plumbum. Okay, so this is in electron volt. Okay. So we have also discussed about Einstein theory of photoelectric. Okay, so basically he extend the idea of Planck. Okay, so somehow this E, the energy of the photon of the light, okay, is proportional to the frequency. Okay, it means that for complete formulation, E equals to h times f, where h is a Planck constant. So because f is c over lambda, so we can get that this E here equal hc over lambda, where c is the speed of light in the vacuum. Okay, so if we combine with a relativistic formula for massless particles, so we get that this P is equal to h over lambda. Okay, so lambda is the wavelength of the photon. So basically we have this formulation. It means that the light could have particle properties instead of wave properties. Okay, so this momentum is this one. Okay. So this is we have discussed about Millikan experiment to prove the Einstein theory of photoelectric effect. Okay, and this is for black body radiation. We have discussed also yesterday. I will, some of it I will skip because, well, this book basically is a book for second year student, physics second year student. So we have this Compton effect. So basically Compton effect, as we have discussed yesterday, we have the incident photon, and then we have this electron at rest, so basically this electron coming from the shell, the atomic shell, orbital shell, okay, or this orbital electron of isotope, something like that. So this incident photon somehow scattered the photon and also electron becomes scattered. So this situation, somehow you have to use relativistic formulation, okay? Because Newton, it is not working in Newton. So somehow you have to work in relativistic formulation. So after some computation using the conservation of total energy and the relativistic momentum, okay, so we get this equation 3.49. So this is, we call it Compton wavelength, the Compton shifting wavelength equation, or formula 3.49. Okay, the quantity is h over mec is called Compton wavelength of electron. Okay, so somehow Compton proved that we have a shift in frequency. Okay, we have shifting in frequency. So it proved that we have these particle properties of waves. Okay. Okay, so this is another physical process. This is basically an X-ray diffraction. Okay, so this is outer photon process. We call it photon interaction with atoms. This about excitation and also Bremsstrahlung. Bremsstrahlung is coming from German language. Brems it means rem ya kalau ininya. Brems Strahlung itu radiation. Okay. So basically the radiation coming from what we call it in English, yeah. Break, yeah. Okay, radiation coming from the breaking. Somehow we have to, the electron is passing through the nucleus, the core of the atoms, okay, nucleus. So somehow because the nucleus is positive, somehow it attracts the electron. Yeah. So somehow the electron become deaccelerate, yeah, become slower, and then as the implication, we have this Bremsstrahlung radiation. This is an example of X-ray production, this Bremsstrahlung effect. Also, we have also pair production. So somehow we could use a photon to produce an electron and also a positron. Okay. Is there any question? No? Okay, we will continue for a new chapter about wavelength properties of particle. So this is the picture. I think this picture coming from STM, scanning tunneling microscope. So this is basically an image that has been, well, using computer. We use computer to produce this picture from the data. Okay. Sorry, this is the electron microscope produced image from electron wave that enable us to flash object. Okay. Yeah, STM is more sophisticated than electron microscope. Yeah. So I will use okay. Hello, can you see the full screen slideshow? Hello, hello.
Yes, sir.
Okay. So we have wave-like properties of particles. So the first is about de Broglie prothesis, and then the experiment of Thomson and Davidson-Germer. So Thomson here is the son of Joseph Thomson. Yeah. This is George Thomson. Yeah. So the father also discovered the electron, okay, the proportional of the what we call it, yeah, this E over M, yeah, the quantity E over M, somehow this E over M, yeah. And also he discovered electron, okay. Electron is a particle, but his son proved that the other way around. So somehow this electron could also act as a wave. So de Broglie somehow extend the idea about these dualism properties. So the first effort, we have discussed about these particle-like properties of the wave. Okay. So we have these wave-like properties of the particle. So somehow de Broglie extend the formula I just showed you, that this lambda is equal to h over p. Okay, p is the momentum. Okay, lambda we call it the Broglie wavelength. Okay, if p is the photon, or photon momentum, then we call it lambda is the wavelength, only wavelength. But if P, for example, if is a momentum of a massive particle, then we call it this lambda is the Broglie wavelength. So this is the formula. It's very simple. So this his hypothesis somehow exposed in the very short PhD dissertation in Louis de Broglie, maybe around 7 or until 10 pages. Yeah. It's very short. Somehow his PhD advisor also doubt about the result. Okay. But Thomson and Germer and Jefferson Germer, they employ an experiment separately. George Thomson is in Cambridge doing the experiment, and Jefferson Germer doing the experiment in Bell Labs in New York, using 100 kilo electron volt electron. So it's quite big energy in this case. So the George Thomson have a Nobel Prize because he proved that the electron is particle, while his son, George Thomson, okay, becomes a Nobel laureate because he proved that the other way around, but electron can have wave-like property. So this is basically the picture of diffraction of an electron on the gold. Okay, so this is the main bright. Okay, the main maxima, the central maxima, dark, maxima, dark. This is like the interference diffraction. Okay. So this is, I think, okay, I will give it shortly about Heisenberg principle of uncertainty. Okay, so basically our universe, okay, according to quantum mechanics, we have uncertainty principle. This is, we call it uncertainty principle of Heisenberg. Heisenberg uncertainty principle. Okay, so basically if we have the position, the error of the position times the error of the momentum, somehow it should, the magnitude, this multiplication should be greater than the order of Planck constant. So the order of Planck constant is 10 to the minus 34. Okay. So this is the limit where the quantum mechanics valid. Below this, if below this 10 to the minus 34, so we don't know what the theory. Okay. So basically, somehow this physics and microscopic picture somehow constrained by this relation, this uncertainty principle of Heisenberg. So it means that we cannot have simultaneously the position of the particle and also its momentum. Okay. Somehow you have to sacrifice whether you have to choose, okay, whether you want exactly, you have the exact position or the exact momentum. We cannot take all of them, okay? So in quantum mechanics, not all measurement we cannot do, we can do simultaneously. For example, if we want to measure the position, so somehow we have to sacrifice this momentum, okay? So this is similar to our life, okay? So not, if we have two choice, not every condition we could have simultaneously these two choices. Okay, we could do these two choices. Somehow you have to sacrifice one choice to do another choice. Okay, so life is our choice. Not always in our life, we cannot always do two choice at the same time, or we are doing simultaneously. Okay. So somehow you have to choose and sacrifice this this momentum or position. Okay. So this is the first uncertainty principle. So we have also the second form of uncertainty principle. This is related to the error of energy, standard deviation, this one, delta E. The error of delta E and the delta T is also greater than the order of Planck constant. Okay, so somehow, but the physical meaning of this uncertainty principle somehow different from this X then NP. So this physical interpretation, it means that we could have a small amount of energy at very short time. Or in other words, we could violate the conservation of energy only at sort of time, very short of time. Okay. This is the second form of Heisenberg. Okay, so basically this uncertainty principle we could also explain using Gedanken experiment or thought experiment. So if you, for example, imagine that we have the incident particles where we have n electrons, for example, and then they passing through this slit, okay? So we will have this diffraction pattern here, okay? So this diffraction pattern can only occur if the width of the slit A is proportional to lambda, where lambda is the Broglie wavelength. Okay, so this basically, okay, this is outside the curriculum, okay, this atomic model of Rutherford Bohr. Is there any question? Any question? Okay, let us continue for the book, yeah. You could also, okay, this is the book about this, the Broglie hypothesis, okay. So basically this one, okay. So this is, for example, the comparison between the Broglie wavelength of 1,000 kilomobile, a car, traveling at 100 meter per second. It's about 200 miles per hour. And then the bullet, and then this electron, yeah, with the kinetic energy 1 electron volt. Oh, sorry, there is also E here. An electron with kinetic energy 100 mega electron volt. So you see that for the first case A, okay, the Broglie wavelength is around 10 to the minus 39. Okay, so this order somehow is less than 10 to the minus 34. Okay, so somehow we cannot use, it means that we cannot use the quantum mechanics in macroscopic scale, because the wavelength of the Broglie wavelength is less than 10 to the minus 34. Okay. For B, for example, a bullet, a 10-gram bullet traveling at 500 meters per second. Yeah, we could. Yeah, it's almost the same as the magnitude. C, a smoke particle of 10 to the minus 9 gram moving at 1 centimeter per second. Okay, we could also. This is D. Okay, so you see that this is D. For example, we have an electron with kinetic energy 1 electron volt. Okay, so we get this lambda. It should be 1.2 nanometer. Nanometer. It's 10 to the minus 9. Okay, so if we want to see the diffraction properties or wave-like properties of the electron, so somehow we have to use the slit of the width 1.2 nanometers, okay, in order to have the to see the wave-like properties of the electron, okay. But for synthetic case, I mean, we could not make such a width of this wavelength, okay? So the width of the slit, okay? So somehow we have to use the crystal in this case. So somehow we have to think that you could use the crystal to obtain this lambda. Okay, so this is the order where we could use the effect of diffraction of the electron. So yeah, so usually the experiment of de Broglie, they use mostly X-ray, X-ray diffraction, and also for George Davison-Germer method. Okay, is there any question? Question? Sorry, do you know, sorry, just a moment. Okay, so this picture is produced by, compiled and produced by the computer, okay? So we get these images. So we use this diffraction of the electron. Okay, this is again the uncertainty principle. So I think we have done about the lecture. I think this is the last lecture. We have already discussed it. Unless you have a question. If not, we stop here. Hello, hello. Hello. Any question? Any question? Any question? Any question? Anyone? No. Okay. So this is basically how to compute the standard deviation of momentum, yeah, for example, in statistics, but we omit the derivation. I think it's not